Okay, so what I want to do to kick things off is on the next slide put together a graphic to kind of summarize where we're at with the state of the art in terms of security for embedded systems. And it looks like this. And my point here is that with respect to embedded systems and security, we're stuck in the 70s, right? The disco era. And why is that? Well, the reason is because we're still using the same tools and techniques for building embedded systems that we've been using since then. So generally this means doing development in C or C++, building using new tools. If you're lucky and you've got a JTAG header on your board, you can use GDB to debug it. Otherwise, you may be blinking LEDs or sending data over the UART. So although we're still building systems the same way we've been doing it for decades now, the complexity of embedded systems has grown exponentially. So there's a name for it, right? It's fashionable now not to say embedded systems, but cyber physical systems. And the emphasis here is that what we think of as embedded systems really has grown in terms of how much they're networked and the complexity of the system. So if you take a modern automobile, for example, inside a modern vehicle, there are dozens, maybe up to 100 now, of electronic control units or ECUs, so microcontrollers scattered throughout the vehicle. And they're all networked together on data buses, primarily CAN bus. And there's also a whole bunch of external interfaces. So radios connecting to everything from OBD2 port for the mechanics to plug into, short-range radios like Bluetooth, long-range telemetry systems, entertainment systems, and so on and so forth. So it's not surprising then, since we essentially have complex network computers on wheels, that this is a ripe target for attacking. And it's now pretty broadly known, some of the early work happening in 2011 and even earlier, that we can hack into automobiles. So there's a New York Times clipping, also more recent work by Charlie Miller and Chris Vauslek. So here's a table from some of the work from University of Washington and UC San Diego that was mentioned in the New York Times article. And I really like this to point out a couple of points that have been made here already today. So the first thing is that, so this is a table talking about all the ways that they're able to penetrate a modern automobile remotely. So through these different interfaces, like things like short-range radio and long-range wireless. And the first thing I want to draw your attention to is the full control column. And what this means is that no matter how the attacker got into the vehicle, were they able to take over any other functionality in the system? So, if I came in through Bluetooth, I'm still able to disable brakes, still able to lock the seatbelt, still able to change lane assist, et cetera, et cetera. And in every case, it's yes. So it's a really squishy insides, right? Like once you get in, it's game over. The second thing I want to draw your attention to, and this was mentioned in the keynote at the beginning, is that what kind of new esoteric security vulnerabilities did they use to get into these systems, right? Well, none, right? It's buffer overflow, buffer overflow, buffer overflow. So, we've got a new, more complex system, but it's the same old problem that we've known about for a long time. So you could say, well, aren't these solved problems? Don't we know how to address them? And there's approaches like sandboxing, things like hypervisors and Chrome native client. These are open source ways to sandbox. High-level programming languages with powerful type systems that are, in particular, type safe and memory safe. So two ones that I like, functional languages, are OCaml and Haskell. And we've got a number of verification tools. But I would say in the space of embedded systems, these are not sufficient. And why? Well, first of all, even though it's the modern era, we still use very small impoverished microcontrollers. So everything from 8-bit microcontrollers with just a few kilobytes of RAM and flash for program memory, and without any kind of virtual memory system. And even though a microcontroller might be this small, like an Arduino, for example, people have developed, full autopilots that fit on these things, with just a few kilobytes of RAM. In contrast, something like Hello World in modern Haskell, you compile it down, it's about, requires about a meg of RAM to run and a meg of size for the executable. Not to mention unpredictability in the runtime system for garbage collection. And furthermore, even if these systems are really small in terms of lines of code, they can be extraordinarily complex. You've got interrupts with device drivers. You're running on an RTOS, so you might have high levels of concurrency with periodic tasks and sporadic tasks. And so, and not to mention, linking in libc. So modeling and verifying these systems post hoc is very, very difficult, even if the code sizes are small. If our problem's not hard enough, additionally, in these embedded systems, it's not just like I have to worry about network security or crypto or control systems. Everything's thrown in together, right? So this is a block diagram of a autopilot, and I'm not going to go through it, but I just want to draw your attention to give you a sense of the complexity of the kinds of properties that the diversity of properties we have to worry about. So, statically linked into one binary, you have to deal with a device driver correctness, sensor fusion, so, Kalman filters. We've got control laws, so deal about, the correctness of dynamic, the vehicle dynamics. The comm systems, networking, crypto, and all this is together, and we want to reason about the correctness of all of this. So, as was mentioned, to address this and see if we can live up to the challenge or at least make some progress, DARPA began the High Assurance Cyber Military Systems Program. So this is the brainchild of Kathleen Fisher, who's now at Tufts, and she was the original program manager. And we were one of the performers, and we worked with a team that included Rockwell Collins, University of Minnesota, Boeing, and Galway, where I'm at. And so the idea was, let's start small. Let's try out to build, if we start, take a greenfield approach, and let's try to do things the right way and build secure systems from the ground up. Can we do this for small systems? Think like quad rotors. And then work with Boeing to transition this to large, complex systems. In this case, they're unmanned Little Bird, which is an optionally piloted helicopter. So a human can fly around this helicopter, or it can just fly on its own. So what I want to do is just tell you a bit, give you a sense of the story of how we went about this. So let me take you back to the beginning of the program. So it was a long program, it was about 4 years long. But at the beginning, we knew we had to address multiple airframes. So quickly moving from small autopilots to large military systems. We were developing for brand new hardware, so boards that we would be manufacturing as part of the program. And we wanted to be able to compile our applications to multiple operating systems. So for example, in terms of the real-time operating systems, we used FreeRTOS, which is a available RTOS to do some initial prototyping. But in this project, we were working with NICTA, as mentioned in the morning keynote. They developed SCL4, which is a formally verified microkernel, which we also wanted to target as they were developing it, as well as their verified RTOS called eKronos. So we need to target multiple operating systems. OYA developed a fairly sophisticated autopilot, so all the application code. Develop a ground control station to communicate with the system with an embedded encrypted data link. And we wanted to also have some properties about the system so that we could give to a red team, for example, to say, hey, here are the claims that we're making. And we wanted to have some architectural models to explain at a higher level what the system's supposed to do in terms of the hardware and the network buses. And we were stuck in the middle, so developing this system. And the approach we took was one of building domain-specific languages, or DSLs, so that we could generate from a family of DSLs the security properties, the architectural models, and the software. And so this is what at the end of this, this was given to a red team in an iterative fashion. And I'm kind of spoiling the surprise, but they said this is that it was free from the normal defects that they found. So I'm not going to claim it's perfectly secure, but it was more hardened than any of the other systems that they had looked at in to benchmark the kinds of security that they see in these systems. And as one government official remarked, this was the most secure UAV in the world that we'd built. And by the way, we did this in 18 months. Okay, so what I want to talk about is how we built DSLs for approaching this problem. So at Galois, we are big fans of functional programming and in particular Haskell. And so we thought, wouldn't it be nice if we could do embedded programming using the benefits of Haskell? So you get a powerful type system, type inference, type checking. It's a pure higher order language without side effects. And you get the modularity and the composition that functional programmers have come to know about and love. However, as I already mentioned, I can't fit a Haskell program on one of these embedded microcontrollers. And so, there's a couple options we could consider. One would be writing a whole new language from scratch. This would be a la kind of, if you squint, you could think of Rust as taking this approach. And when we began this project, actually, Rust was a pre 1.0 release. So there's just not the time to do that, to basically do a compiler development from scratch. The other approach would be, let's try to hack down the runtime system. But the runtime system, the dirty little secret of these functional languages, right, like is, we've got all the purity, and then we've got 50,000 plus lines of C or C++ sitting underneath that functional language to implement the runtime system. And, trying to do that in a short order and guaranteeing correctness is just too difficult. So the approach we took was one of building an embedded DSL or EDSL. So the idea here is let me build some combinators in my functional language, and this is going to implement my safe programming language. And what this will do is it'll generate safe embedded C. So the nice thing about taking this approach, this EDSL approach, is that your new language that you're designing is just, quote unquote, a library in Haskell. And you get a bunch of things for free. I get type checking for free. I get all the syntax and parsing for free. And most importantly, I get to use the host language, Haskell, as a type-safe, Turing-complete macro language. And I'll talk more about that in a few moments. So the language we developed is something called Ivory, embedded in Haskell. And you can think of it as a high-level functioning programming language for low-level embedded systems. And there's a few features that I'll draw your attention to. So one is it's, effectively it's a safe C language embedded in Haskell and specialized for embedded systems. So the primary, there's a few trapdoors, but the primary use, it is, sub-Turing complete. However, the way we are able to get usability, as I mentioned, is this type-safe macro programming. So I can kind of fake Turing-complete programming at design time, at compile time, by using Haskell, and I'll give you some examples. And we've also got some verification tool integration, including symbolic simulation, a theorem proving backend with ACL2, as well as automated test case generation. Okay, so let me just give you a quick taste of the language, just so you can concretely see what it looks like. So here is a loop that operates over an array, adding a value to each element in the array. So first I'm going to show you the type. I've written it here explicitly, but there's actually type inference for free, so I didn't have to explicitly write this. And I've got a type level list, and it takes two arguments corresponding to the two arguments that the function will take. So the first is a reference. So this is a guaranteed null pointer with a type variable s, which means the allocation scope of the array. In this case, it's a type variable. It means it could be locally allocated or globally allocated. It's a pointer to an array with 4 elements, and in each element is a unsigned 8-bit value. And it takes another unsigned 8-bit value and returns void. So if we walk through this, in the implementation, I have a lambda binding that corresponds to the two arguments the function will take, if you think of it as a CF function, the array and the value. And then we have a combinator array map, which maps over the elements, so guarantees I can't walk off the array. And for each index, it's going to dereference a value, and this is guaranteed null by type checking dereference, and then store a new value there. Okay. Now, as we did this, even if you're a Haskell programmer, there's a lot to take in there. So one of the things we realized, especially as one of the goals of the program, is to transition this to engineers, systems engineers who are not Haskell developers. we wanted a concrete C-like syntax. So we developed a concrete syntax over this where if you squint, it looks quite C-like. So here's the same function again in a concrete syntax, and there's just a few differences I'll call out. So first of all, in C, of course, you pass in the length of the array that you're going to map over. We don't have to do that in the concrete syntax. We still have this map operation, which instead of having a for loop over the array. And as I mentioned, I've got different allocation scopes, and so I can decorate a pointer and say, this is, for example, global allocation. And this is really important. So when we started the program and did not have a concrete syntax like this, and we're trying to throw this over the wall to C++ developers at Boeing, there's just no way that they're going to be able to use the language. So, but by doing this, by having a C-like syntax, we could throw it over the wall. And as far as they were concerned, this was basically, a strange C with different type errors and some cool macros. And so they were able to basically rewrite many, many thousands of lines of codes, rewriting their flight controller and mission computer with very little help from us. Okay, so I've mentioned this idea of type-safe macros a few times, so let me just give you an example. So the language itself is very impoverished. So for example, in Ivory, there is just one construct for doing control for if and else control, so there's no conditional statements. And so you can have, if you've got a lot of nested if then else's, it can, if you're a Lisp programmer, this might look familiar, but it can be quite cumbersome. Now, one of the benefits, though, is that the developer, because it's an embedded DSL, does not have to be stuck in the paradigm of writing with just the operators that we provide. So, for example, a developer with just literally 4 lines of code can define a data type, as cond for conditional, can define a couple of smart constructors. So here we've got a fat arrow that returns something that is equivalent to the data type, and then constructors over lists. And what it'll do is construct new syntax in the language. And so Ivory has not changed at all, but I'm able to now generate a much more pleasing, depending on your perspective, conditional expression that is equivalent to the original without having to bake this into the language itself. Okay, so here's a very simple example. A more complex example is one we used in developing sensor fusion. So automatic differentiation is how many people are familiar with automatic differentiation in programming? Okay, so it's a maybe underappreciated but fairly ubiquitous approach to do automatically computing differentiation for programs that's neither symbolic differentiation nor numeric approximation. And the idea is that I can automatically transform a program to compute the differential using different techniques. And this is quite useful for writing programs that have to deal with continuous dynamics. So let me just walk you very briefly through forward automatic differentiation. And so the idea is I'm going to walk through a program, automatically transform it so that I'm going to take variables and replace them with pairs where I keep track of the original value and the differential with respect to that value. So as there's a few rules. So for example, to do addition on these pairs, I'm going to define an algebra, so I just do addition pointwise. For multiplication, I've got an expression like follows, where I multiply the original values, and then like you do in differential calculus, I'm going to take u v prime plus v times u prime, et cetera, for the arithmetic operations. And so, like as a little example, if I got f of x equals x plus 2 times x plus 3, I can transform it. Variable, if I take the derivative of the variable, I get 1. Derivatives constants are 0. And follow the rules, I get the original value plus the differential, the derivative. Okay, so what does all this mean? Well, because in Haskell we've got type classes, and which means I can do operations as long as anything satisfies those type classes. In particular, so for example, I've got a num type class that tells me how to do addition, subtraction, et cetera. If I have any instance of this, including the AST for the Ivory language, I can use these operations for free. So in Haskell, like in other languages, automatic differentiation has been defined. And because of this, I can use the libraries that compute these things for free to automatically develop new C code that computes the derivative. And so the upshot of this is, for example, in developing our inertial navigation system, we can write just a few hundred lines of code and then use these techniques, for example, to compute the Jacobian matrices, which are used in the Kalman filters we developed. So this is just to give you a taste of the ways we're able to build these abstractions up without having to bake them into the DSL. We can keep this small and lean, allowing us to do things like static analysis, et cetera, on the language. And not have to extend it to a general purpose language. Okay, let's see. So what I'm going to do is I'm going to just briefly talk, but not go through in detail given the time, about the approach we took to concurrency. So, this is all well and fine. We can use Ivory develop to write our application code for our individual threads in the system, whether it's on SEL4 or on an RTOS. But when you start looking at the problem of all the glue code, all the interprocedure communication, handling the interrupts, we start running into all this was written in handwritten in C, and it becomes a nightmare. And this is a problem even if we're developing on a formally verified operating system. So, if I'm writing everything by hand on SEL4, even, the kernel, if you say I want to communicate between two threads that shouldn't communicate with each other, it will perfectly let you do that, right? So it's up to you to have the right kind of specification requirements. And furthermore, we want to easily be able to port from one operating system to another. So the story is exactly the same. We built another DSL on top of Ivory that handled generating things like the IPC and the glue code to guarantee safe concurrency. The implementation uses a Hoare monitor style approach. And we can also do this to generate architectural models. So in particular, we generate models in the AEDL, which is an architectural modeling and design language, which allows you to do verification at the architectural level. Right, okay. So I'm going to skip through some of the examples of this. And let me skip here. So with Ivory and Tower, we've got a number of backends. So targeting POSIX, as I mentioned, FreeRTOS, and AEDL, and then there's an in-progress target to the SAL model checker. And through AEDL, we target eChronos and SEL4, which I mentioned were verified operating systems. And this is what we call our trusted build, which we used in the program. And this tied into a larger story of analysis, which I won't go into, of using various tools that are developed that are in the open source domain for doing things like model checking at the architectural level, but also doing requirements analysis. So for example, this Resolute tool allows you to develop a safety case. So I'll always have informal portions of my program that I want to be able to talk about why I believe they meet the requirements, even if I don't have a formal proof. So by building a safety case, you stitch together the informal with the formal. Okay, so this is just a eye candy slide. We took this, our project on a road show. So this included probably being the first UAV to fly the first pictures in the courtyard of the Pentagon. What we learned there was that the most important rule is do not step on the grass at the Pentagon. And we also, there was a briefing of this on 60 Minutes. So here we are flying with Leslie Stahl, and there's Kathleen Fisher in the foreground. And as I mentioned, in the red team analysis, they were given all the code, all the requirements, all the specification, the hardware, and 2 months to analyze this, and this was actually an iterative process. And the main result, they said, we cannot penetrate the network in the vehicle. And there's definitely, issues that they discovered. So things like, for example, we left the debugging port open, which, if you had physical access, you could attack. And there was an unverified assertion. So we were especially brave for assertions that we had not verified away at design time. We still left those in and said, please let us know if you trigger any of these. So as I mentioned, this is much better than the baseline systems that were analyzed in both open source and DoD systems. So I just want to end by giving a couple of kind of lessons learned from this project. So the first is that while this was a formal verification project, it's also a research project, and that was at odds in some sense, right? So we know how to write high assurance code even without formal methods. It just takes a long time, right? People were writing code for the space shuttle before there was static analyzers, before there was model checking and widespread use, and it's fairly bug free. But you're talking a very much lower programmer productivity. And you can't expect formal verification to magically make the process go faster and let you elide the other kinds of things to improve your system. So one of the things is that, if I'm developing around a verified microkernel, I need to make sure that the rest of my system has a verification story for it as well. I can't just assume that, I verified this one little piece and everything is going to be fine. And we need to do all the easy stuff in addition to verification, right? Regression testing, fuzz testing, continuous integration, code reviews. And so this is why, to build truly secure systems, you can't just rely on formal verification, even though it's a critical part. As we've heard a number of times today, we need to do the other things. Like, one of the simple things that we did, which, is filtering the network communications on this thing, which had a huge effect. So originally, for example, in open source autopilot, there was a convenience, quote unquote, of allowing you to reflash the code over the data link with the ground control station, which is, really great if you're developing by yourself and you just want to, you don't want to have to plug into the USB to reflash the code. But you know what? Anyone who has access to that can do it even in flight, for example. And also we need to handle all possible errors in the interfaces. Tool integration, this is an unsolved problem. There's multiple tools, and how do we pull them all together to combine the analyses and get a global view of a system is still a very difficult problem, and one that has to be addressed. And there's definitely a number of things that we did not, I don't have a good answer to. So, for example, this is a system that is hovering above you with sharp edges. And when something goes wrong, you might, if I have an IT system and someone's attacking my server, well, I might just power it down. That's not going to work for a UAV. That's right. You don't want to just power it down. So how do I gracefully do a failover if there's a security vulnerability discovered in real time or I'm under attack? Okay, everything's open source. We've got a website for the language and the autopilot, so you can build everything yourself and go fly. And with that, I'm happy to take questions. Thank you. Yep.
Why did you generate through AEDL? So I expected it to be the other way around, right?
So that's a good point. So in fact, we did two different versions. One from AEDL, where that was the primary design language. In the other direction, so in fact, so this tower language I glossed over is, you can think of it as a Haskell version of AEDL, which is morally equivalent. One advantage of going the other direction is that it enforces, so because Tower is tied, has the same, shares a type system with Ivory, it guarantees that every time you recompile your system, I rebuild my architectural model of the system. And so I don't have this possibility of my architectural model that I might have done some nice formal analysis on drifting apart from my compiled code. So that's one advantage of going that direction. Okay, all right, thank you.